So hello everyone. So I told you last day I'll create a video for the question 4. So you see here this question is in the tri-adiabatic model of the atmosphere. In addition to the ideal gas equation, air is also assumed to obey the equation P over rho n equal constant. So this is actually similar equation like what we know for the ideal gas equation P equal rho RT, so that I will show you later. In the n, this is the constant, it is given 1.4. So now if the condition at sea level are standard, like this pressure and 15 degrees centigrade, we need to determine the pressure and the temperature at an altitude of 4,000 meters above sea level. So that's our requirement. We are going to calculate the pressure and the temperature at 4,000 meters of altitude. Like this is our ultimate target. So we are going to calculate pressure and temperature at this case. So if you can remember, we said the pressure varies along z-axis always, and we know this expression dp. You see, this is the z-axis, so this dp and dz equal rho z, negative rho z. So z is always goes to the downward direction, and the z-axis is always in the vertical axis. So this is the positive directions. Now if we do some simplification here, we can just put this rho to the left hand side, like dp and this g rho, and then it will be g, and this is the gravity, this term gravity g, and this dz, right? So that's we just simplified that equation. Now here it is given p over rho and it is equal constant. So we say constant, it is equal constant c. So can we write something like that? P over rho n, it is equal c over rho. This is the same thing. You see this is constant c, so we just divide by 1. That means this is the same thing, p by rho n equals c. Our ultimate target is we want to simplify this equation, and we want to get an equation for density. So P is the pressure, this is rho is the density, and C is constant. So let's say if we do some more steps like rho and C equal P, see some cross multiplication, rho and C, so this one equal P. So that means we can write that rho n equal P over C. So we just did some change from left and right hand side. So what I said initially, our target is we actually want to get an expression for rho. So we got here rho n equal P over C. So if it is our target to get rho, so we found we have an power here, so we multiplied 1 over n in both sides. So if we multiply 1 over n here, so then you see you can simply just eliminate these two terms, n and n, then you will get it as in rho, so P over C and power 1 by n. So let's say this expression, it is equation A, and this expression, this is equation B, because we are going to use all of those later. So now at sea level, we have, if the condition at sea level are standard, we need to determine the pressure and temperature at 4,000 meters above sea level. So we know these gas equations, P equal rho RT, that means P is the pressure, rho is the density, gas constant, temperature. So you see from here, I told you earlier, this is kind of similar thing of this gas equations. So if we divide this rho, okay, if we divide this rho in both sides, so it will be P over rho, and this is rho RT by rho. So then you can eliminate rho and rho. So it's something like that. If we say rho, this is RT over rho. Then we can just simply eliminate this row and this row, so it will be RT, right? So it will be RT. Now look here, if we said, okay, so one thing I should say, R equal the gas constant and T equal temperature, that should be constant. So that means P over rho, this is also constant. That's it, the same thing, P over rho equal constant. So we can say now, if we do more simplification, then we say rho equal P over RT, and we know P equal 1013, we know this gas constant, and the standard temperature is 15 degrees centigrade. You see, 15 degrees centigrade. So 273 plus 15. So if we do calculation, then we'll get the density is 1.226 kg per meter cube. So now we have the density at sea level, right? We got the density 1.226. So look, we know the pressure, we know the density. So if you see this equation A, right? If you see this equation A, we know P over rho n equal constant C, like this, P over rho n equals C. So can you write C equal P over rho n from here? You see, we wrote from equation A is C equal, this C equal P over rho n. So this is from equation A. I told you, okay, we're going to use this later. So we know this pressure, we know this density, and the n is actually constant 1.4. So then we got this constant like 76,160. So that means now we have pressure, we have the density, and we have the constant C. So we know all of these values. And now look, see, our ultimate target is to calculate the pressure and the temperature at an altitude of 4,000 meters of sea level. Okay, so now if you see here, so we got another equation for the density. So we derived from these equations, especially for the density, and we got rho equal P over C1 by N. So this is equation B. So if we use this equation here, so this equation B, so what I got, rho equal P over C1 by N. So we know this pressure. Sorry, we actually need to calculate the pressure, right? So we know this constant. We already calculated this constant, 76,160. So put this on here. You know this n 1.4. So now if we substitute every values here, then we will get an expressions like rho equal 0.03258 and P to the power this. So we got this expression. This is a function, this is an equation which is function of the density and the pressure, right? So you see, this is actually the term for pressure, and rho equal density you all know. So from the equation B, we just derive these equations. So this is a function of pressure and the density, and our ultimate target is we actually want to calculate the pressure and the temperature. So here we got this expression. So we know the density function, and this equation is this function of pressure P. And now you see, if you can remember, initially we wrote dP by dz equal rho z. So I'll go back there. Yeah, so this dP dz equal rho z. So we wrote dP d rho equals z dz. So we wrote the same thing here, dP, because our ultimate target is, you see, we got this function which is combination of pressure and the density. So our ultimate target is to calculate this pressure at 4,000 meter level of altitude. So what we did, we wrote here dP d rho equals z, and then we just substitute this value, like this pressure and the density equal, you see, 0.03258 and the pressure 0.7148, and we know the gravity 9.8 dz. So now here nothing means we have, maybe it is multiplication of 1 into dp, right? So 1 into dp. So if I just do some calculation like 1 over this value, so we will get it is 13.2, okay, and then dp over p into 0.7148. So the one thing I should tell you, it will be actually we need to do one more steps here, but I believe this is very simple calculation. So what you need to do is this is dp over this and equal 9.8 something. So if I say this is over 1, something like that, so we can do cross multiplication like this part, and this part. So at first you need to multiply this value 0.03258 into 9.8, and then you divide from 1, and then it will be 313.2, and then dp over p 0.7148 equal, it will be negative dz, because we already multiplied this 9.8 with this one and then we divide it. So now if it is the case dp over dz, if we want to get this pressure, and you all know this is the differentiations, this is called the rate of change, or the so what we need to do is we need to integrate this one. So we will integrate the both end, and for this pressure the initial is, I explained last day, it is p naught, and this is the pz, and this is z naught and z. This is the upper limit and the lower limit. So what we wrote here, 313 p naught to pz, p, if you see here dp over p 0.7148, so you can write it is p inverse 0.7148 or dp. So see, let me write something maybe here, let me write just that on here. So it is something, if I write here, if we know something like dx over maybe x n, if we have a term something like that, dx over dn, so we can write it is x to the power negative n and dx. Okay, so that we can write dx over dn, so we can write x to the power negative n and dx. So that way we wrote this term. So p, it was p 0.07148, so it had p negative 0.4748 dp, and if we integrate dz, you already know from last class, so I will write here integration of dx, it is equal, it is equal x. So it dz equals z and the power z to z naught. So now we need to do some calculations like what we did previously. So this may be p dp, so it is kind of we can say x and dx. Okay, so x and dx, so if I write one dx here, so x and dx, the integration formula is x n plus 1 over n plus 1, so it should be this p and this value plus 1 over this value plus 1 and then this limit, and it will be like, so from the previous term we need to replace the limit, so z equals z naught. So now simple simplifications, we will see from this term to this term what we did, we just replace this p by using this upper limit and lower limit, so it should be pz, this term plus 1 negative, this p naught, so p naught we need to replace here and these terms, and over this is as usual. So we got here negative z and this negative, this minus sign, it should be plus z naught. So we got this term now. Now actually we need to do just simplification, nothing else. So now what we did, we just did some calculations, like it was 0.7 and something like plus negative 0.77 and something plus 1. So if we calculation, it will be something like that. We substitute the value of pressure P, and if we assume that okay, if we need to calculate the pressure at 4,000 meter of altitude, so what we did, we said okay, this is actually the pressure at 4000 meter, and the P naught, it was the initial pressure, so that's why it is the given like atmospheric pressure. And similarly, if you see here, this is actually for the value of P naught. P naught just means we substitute these values here, and the Z naught, it should be actually the 0, the initial 0, and the maximum is 4000. So if we substitute all these values, so then we will get this term point. So this is here just as it is, and from this term to this term, what we will do is we will multiply this 4000 into this value, because we say this is by 1, so we can do simply the cross multiplication. So you see here we did some multiplications, so then we will divide this 313 in both sides. So if we divide in this side, we can eliminate this one, so it will go to the right hand side like this. And then now we have P this negative this value, so if we put this term to the right hand side, it should be positive. You see, now this P equal this term negative this term plus this term. And finally, our target is to calculate the pressure at 4000 meter of altitude, but we have this power 0.2857, so we will multiply in both ends, like 1 to the power n or something like that. So then this power, it will go to the other side, like 1 by this. So it is something like what I said previously. We have xn, so xn, if we want to get only x, then what we will do, we will multiply one term, maybe 1 over n, and then you can eliminate this term, you will get x. So we did the same thing, we just multiplied to 0.2851 in this both side, and then we got this term. So now you need to use the calculator. So if you do some calculation by using a calculator, then you will get this pressure is this Pascal. So we got the pressure. Now we need to calculate the temperature. So we know the gas equation at sea level is P equal rho of T. So we say this is at 4000 meter of altitude. So then the temperature T will be P over rho R. So now we know the pressure for 4000 meter of altitude. We just calculated, this is the value. We know the gas constant, this is constant. We need to calculate the temperature, but we don't know the density at 4000 meter of altitude. So we know this equation, rho equal P over C1 by N. So C is constant, N is constant. So if we substitute the pressure for 4000 meter of altitude, we calculated just a couple of minutes back. So if we put it here, then we will get the density for 4000 meter of altitude. Then we will have everything, and then we will be able to calculate the temperature. So let's see. So now what we did, we just calculated the density, right? So then we just substituted the pressure. All of these values, when we substitute all of these values, we got the density. And then by using that formula, like T equal DC 4000 meter, so P equal rho RT, right? So this is the the general gas equation, rho R and T. So and we know T equal P by rho R. So this is the pressure, right? And the gas constant, this is the density. We just calculated this density here, and we got it is 249 Kelvin. We need in centigrade, so subtract from 273, and it will be negative 424. So that's actually the temperature. So we calculated the temperature and the pressure at 4000 meter of altitude. Okay, so I believe I already sent you this worked out solution. I believe you got the solutions, and you will see the detailed step-by-step calculation there. And if you still need help, yeah, I believe now it should be clear. So thanks for watching.